Welcome to the first in a short series of videos on the chemical bonds and the formation of compounds. The previous set of videos, linked in the description below, investigated electronic structure and the periodic table. You will now see how this can be used to determine what types of compounds can be formed. Atoms, particles with identical physical and chemical properties, will combine to form compounds, particles with new properties, and the type of compound formed depends upon the type of bond. This is directly related to the electronic structure of the atom involved. Broadly speaking, there are two types of bonds. The first type is ionic. In this case, one atom will give up an electron to become a positive cation. A second atom will receive that electron to become a negative anion, and the positives and negatives will attract, forming ionic compounds or salts. These are formed by exchange of electrons. Other compounds. Electrons wind up being shared in what's known as a covalent bond. These compounds are called molecular and arise from the sharing of electrons. In either case, bonds are formed by either giving, sharing, electrons, and this is done for the same reason. The important thing from the periodic table is that atoms are trying to achieve the electron configuration of the nearest noble gas. This can be given by either giving electrons, taking electrons, or sharing them. The type of bond depends upon where the atom is or the element is on the periodic table. Also, it's worth noting that these simple classifications are also the extremes. In reality, bonding occurs between a gradient between purely ionic and purely covalent. For an introductory video, this fine point will, for now, be ignored. The periodic table. One can tell what type of bonding is most likely to occur. This has to do with periodic trends. Essentially, the main periodic trend, you have type of elements present. Most of the periodic table is composed of metals. Metals are malleable and ductile. They conduct heat and electricity and generally form positive cations. All the way to the right are nonmetals. These are brittle and insulating. They form anions when they ionically bond, but are also capable of covalently bonding, sharing electrons between each other. The thin strip in the middle, the nonmetals, or semimetals rather, are actually incredibly technologically important. Those are your semiconductors, which make most modern technology possible, and generally bond covalently. Within these, there are trends on the periodic table. The first and partly most obvious is that atoms have different sizes. The atomic radius. As one goes down any given column, one is adding more electrons, more protons, so it's fairly obvious that the atom is going to be increasing in size as you go down a column. Less obvious, however. As you go across a row, you are now filling in an energy level. The more electrons in the energy level, the closer it gets to being completed, tends to cause a stronger attraction with the nucleus. Therefore, the atoms actually shrink as they go from left to right. Since bonding has to do with either giving, taking, or sharing electrons, the strength at which those electrons are held directly impacts what type of bond you're going to have. Generally speaking, the further away a positive charge and a negative charge are, the attraction decreases. This leads to three consequences with regards to atomic radius. Properties of atoms that indicate what types of bonds they're going to form. The first of these is the ionization energy, the amount of energy required to remove an electron. The second, electron affinity, the amount of energy that's released when an electron is added. And thirdly, electronegativity, the ability to attract an electron. Again, as the attractive strength is inversely proportional to the distance, you wind up with, in all three cases, an opposite trend to the radius. All three, ionization energy, electron affinity, and electronegativity, will decrease as the atom gets larger. So it will decrease from top to bottom and increase from left to right. The simplest way to remember these trends is the fact that the closest to the top and furthest to the right is going to be the most electronegative and have the strongest electron affinity and the highest ionization energy. Since the noble gases do not react, that leaves us with top right. Fluorine is simply the most. It has the highest ionization energy, the highest electron affinity, and the highest electronegativity. As one moves away from fluorine, all of these properties are going to decrease. These properties are what indicates how an atom is going to react. For the first type of, simplest type of compounds to imagine, ionic compounds, we've already seen the trend based on the noble gases. Group 7, being one away from group 8, will all form anions with a -1. Group 6, being 2 steps away from group 8, will form anions of a charge of -2. Going to the left, group 1. To the nearest noble gas, it's easier to go backwards 1 than forwards 7, so everything in group 1 is a +1. And for the same reasoning, everything in group 2, the alkalines, will form a cation with a charge of +2. Of the elements that also ionize the transition metals, there are no easy trends to determine. Essentially, one keys on the fact that you know in an ionic compound, group 1 is going to be +1, group 2 is going to be +2, 6 is going to be a -2 charge, and anything in group 7 is going to be a -1 charge. And you will see in later videos linked in the description below, you can use this information to determine what's going on with all of the other elements in the compound. So thank you for listening, and as I said, continuing in this series, you will see how ionic bonds are formed, how ionic compounds are named, and also how covalent bonds are formed and how the shape of these compounds indicates their reactivity.